The twin paradox, a notable thought experiment in special relativity, fundamentally involves identical twins with differing experiences of time due to their disparate spatial circumstances. One twin embarks on a space journey at high velocity and returns to Earth to find that his stationary twin has aged far more. This seems perplexing as both twins observe each other to be in motion during the period of separation. This leads to a naive misapplication of principles of time dilation and special relativity, as logically, each should perceive the other to be younger. However, this quandary can be unraveled within the established framework of special relativity by identifying distinct inertial frames for the outbound and inbound journeys of the space. Traveling twin. This twin can also be considered to have experienced acceleration. Becoming a non-inertial observer, both perspectives indicate a lack of symmetry in the space-time trajectory of the twins. Therefore, the twin paradox isn't a genuine paradox, i.e., a logical contradiction. The resolution of this paradox remains a point of contention, and theories put forth since 1911 have attributed it either to differences in simultaneity standards in varied frames or to acceleration experienced by the traveling twin. Max von Laue, in 1913, highlighted the switch of inertial frames as the reason behind the age difference. Albert Einstein and Max Born suggested that gravitational time dilation directly stemming from acceleration explains the discrepancy in age. Still, it has been demonstrated that even in the absence of general relativity or acceleration, the effect persists, for instance, when two astronauts synchronize their clocks at a turnaround point. This observation leads to them being thought of as two observers, moving in opposite directions from a common point and exchanging clock readings at the turnaround point. Both maintain constant speed, and their journey times are totaled at the end. Albert Einstein, in his 1905 paper on special relativity, argued that a traveling clock would lag behind a stationary one once synchronized and separated, and that this wasn't a paradox but a natural outcome of special relativity. In 1911, he extended on this idea, suggesting that a living organism moving at light speed would experience time as an instant, returning to its original spot barely changed, while corresponding organisms at rest would have aged significantly. In the early 20th century, Paul Langevin introduced a hypothetical scenario involving a traveler journeying at almost the speed of light, encapsulating the complex concept of relative time in special relativity. According to Langevin's paradoxical narrative, a traveler moving at 99,995, the speed of light, spends a year in a projectile, then reverses course. After the voyage, whilst the traveler ages 2 years, Earth experiences a duration of 200 years. Throughout the journey, constant signals are exchanged between Earth and the traveler, which ties the tale into the category of twin paradox encompassed by the Doppler effect. The differential time aging rates are rationalized by the different signal rates affected by relativity, and the story's asymmetry is attributed to the fact that only the traveler experienced acceleration. Max von Laue extended Langevin's explanation, adding Hermann Minkowski's spacetime formalism to concretely prove the disparity in elapsed time between events. Lord Halsbury, among others, proposed a scenario negating the acceleration effects by incorporating a third party using his clock readings, consequently facilitating the avoidance of these acceleration effects. Even though the tale of the twins seems arguable, neither Langevin nor Einstein considered it a paradox. Rather, they construed this phenomenon as substantiation of relative physics coherence. Imagine a spaceship on a round-trip mission to the nearest star system at 80 of light speed, assuming an instantaneous acceleration to full speed and immediate reversal at the destination. Observers on Earth anticipate the round trip consuming a decade of Earth time, while the travelers, due to the time dilation factor inherent in special relativity, will only age 6 years. This is a transition of a scientific concept into a compelling narrative that enthralls both scientific non-scientific audiences alike. Let's discuss the twin paradox within the context of special relativity. This profound thought experiment involves an interstellar journey embarked upon by one twin, while the other remains on Earth, resulting in divergent ages. When they reunite, all observers would concur on the clock readings. Regardless of the method employed for prediction, the crux of the paradox lies in time dilation, with each twin's perception that the other's clock is slower is argued valid under the principle of relativity. Different resolutions have been proposed, underscoring the distinction between the twins' experiences. The Earthbound twin, remaining in the same inertial frame throughout, contrasts sharply with the traveling twin who experiences different inertial frames. First moving away from Earth and then towards it, this transition incorporates a critical acceleration phase, rendering the twin's frame temporarily non-inertial and clustering a distinctive aging asymmetry. Although the turnaround acceleration of the traveling twin is pivotal in some solutions, it's debatable in scenarios with two separate travelers intersecting at the EA turnaround point. Here, physical acceleration bears no definitive effect, giving precedence to the Lorentz invariant length or proper time interval of a trajectory, synonymous with elapsed time as measured by a moving clock. Consequently, in a Minkowski spacetime, variances in experienced accelerations between the twins are inevitable, regardless of their durations. Nonetheless, the acceleration's impact vanishes in curved spacetime representations of the twin paradox, with both twins freely traversing along spacetime geodesics until they eventually reunite. This paints a broader picture of the twin paradox. Prior to the journey's midpoint, the twin on board the spaceship calculates their Earth-based counterpart's age by measuring the time along the vertical axis from the starting point to the higher blue line. Directly after the journey's midpoint, on repeating the measurement extends to the lower red line. Essentially, a sudden shift in the perception of simultaneous events from the higher blue line to the lower red line occurs during the mid-journey turnaround. This shift skips over a significant portion of the lifespan of the Earth-based twin. A sudden discrepancy arises in the Earth-based twin's age, 64 years in the given instance, as the astronaut switches from the outbound reference frame to the inbound one. An out-and-back twin paradox, Odyssey could involve transmitting time readings from an outbound astronaut to an inbound one, effectively negating the impact of acceleration. Contrarily, physical acceleration of timekeepers doesn't influence the kinetic consequences of special relativity. Instead, uniform inertial motion alone creates the time differential between two reunited timekeepers in special relativity, as per Einstein's original 1905 relativity paper and following Lorentz transformations. In line with the lattice of clocks protocol and Einstein's spacetime diagrams, a sudden return astronaut will observe an inevitable change in Earth time, as per the new meaning of simultaneity from the switch to a different inertial frame, as per spacetime physics by John A. Wheeler. But if instead the astronaut and Earth-based party constantly update each other on the current time via light, speed radio signals, all involved will notice an increasing asymmetry in timekeeping starting from the journey's midpoint. All processes, chemical reactions, biological functions, instrument readings, human perception, coupled with eye-brain communication and force communication, are governed by light speed. Timekeeping exists at every layer, hinging on light speed, and natural delay at even the smallest scale. Biological aging is not exempt from this. It is slowed down in the same way as timekeeping is. Therefore, some theorists opt for a phenomenological approach, pondering what the twins would see if they exchanged regular time, stamped radio pulses, or video feeds or images of them displaying their respective ages. Let's discuss mysterious phenomenon of the relativistic Doppler effect. As one object moves away from another at a significant fraction of the speed of light, the frequency of its transmitted signals, whether they be clock ticks or wavefronts, is perceived as redshifted, or reduced by the observer. For instance, for a source moving directly away at 80 of the speed of light, the observed frequency is a third of the original. In the context of our twins, the static twin receives a slowed-down signal from his sibling spaceship for 9 years, transmitted at a third of the source frequency. He perceives his traveling twin to age 3 times slower over those 9 years. Conversely, they would both observe each other's clocks running a third of their own clock speed, factoring in the light time delay that increases at a rate of 0.8 seconds every second. Both comprehend that the other is aging slower by a rate of 60. Upon its homeward journey, the traveler's clock on the spaceship, previously reading at 1 year after launch, increases to 10 years after launch during the 3-year trip. This gives the impression the clock is running thrice as fast. The observed frequency is now heightened or blue shifted due to the approaching source. At the home base, the viewed mission time post-launch jumps from 9 years to just 3 years upon the ship's return. Again, the clock seems to run 3 times faster than usual. Each twin, accounting for the decreasing light time delay, calculates that the other is aging at just 60 of his own aging speed. The story further illustrates the unusual time discrepancy with XT diagrams, representing spatiotemporal paths of light signals, showing clear red-shifted intervals, Each twin perceives a drastic shift in the frequency of the image received from the other initially. Each sees the other's clock running extremely slow, with the image taking longer to reach due to the increasing light time delay. However, this changes dramatically on the voyage back, when each sees the received image's frequency increase drastically, signifying their siblings' clock running thrice as fast. The story thus explores the mysterious, counterintuitive nature of time as examined under relativistic conditions. For a span of 3 years on their outbound journey, the space-traveling twin observes their earthbound sibling via low-frequency, red, images appearing to age by 1 year. In contrast, through high-frequency, blue, images over the 3-year return trip. The earthly twin appears to have aged by 9 years therefore. At the mission's conclusion, the earthbound twin seemingly aged a total of 10 years. Meanwhile, the earthbound twin watches their space-traveling sibling through slow, red, images over 9 years, observing the space twin age 3 years. Then, in the remaining 1 year until the space twin's return, the earth twin views accelerated, blue, images witnessing the space twin age an additional 3 years. This results in a total perceived aging of 6 years. Thus, the space twin seemingly returns younger, having visibly aged 6 years as compared to the 10 years of aging observed on Earth. It is paramount, however, to delineate the difference between observed and calculated aging. The twins are aware that the images they see of each other originated in the past and are affected by Doppler shift. Therefore, they don't base the other's current age on these images. Instead, if one twin tries to deduce their age back when the image was captured, they need to consider the distance between them when the image was transmitted, factoring in the concept of simultaneity for remote events. To calculate the aging speed when the image was sent, they adjust for the Doppler shift. Just as an ambulance siren sound frequency is altered when heard, the twins would know that the image frequency has been affected by Doppler effect. So, they calculate their twins' aging rate accounting for this change. Similarly, they deduce that their twins' aging rate in all the low-frequency images was reduced for the same reason. Understanding simultaneity's involvement in the Doppler shift calculation is a challenge. However, the space twin could use it to convert the Doppler shifted rate they receive into the slowed down pace of their distant twin's clock, applying this to both red and blue images. If they dismiss simultaneity, they might mistake their twin as aging at the reduced rate throughout the journey, and thus should be younger. But when the space twin returns to Earth, they have to rethink their concept of simultaneity. The calculated image rate, adjusted for the Doppler effect, corresponds to the earthbound twin's clock at the moment the image was sent, not when it was received. As the space twin gets more red than blue shifted images, they should recognize that these emissions were not sent over equal periods from the Earth. Twin hints. Simultaneity at a distance remains an essential consideration. The theoretical phenomenon of time progression variation for the stationary twin versus the traveling twin is rooted in gravitational time dilation. This concept proposes that when an observer perceives inertially moving objects as experiencing acceleration, those objects are in a relativity's context within a gravitational field. As the jet-setting twin embarks on their journey, an expansive gravitational field encapsulates the universe, providing a basis for the differential shift in time using a minimal field approximation. It's determined that clocks tick at a speed of T1 pfc2, with h serving as the variance in gravitational potential. For this particular narrative, PHG, where GE stands for the acceleration of the traveling observer during the journey, and h refers to the distance to the stationary twin as the spaceship propels toward the stationary twin. It situates the twin in a heightened gravitational potential. Foods for thought. The substantial distance between the twins allows for the clock of the stationary twin to seemingly tick faster. Bridging the variance in perceived time, it's worth mentioning that this acceleration is precisely adequate to account for shifts in time simultaneity. This reflection of time dilation is mirrored in both the general relativity solution within a static homogeneous gravitational field and the special relativity solution within finite acceleration scenarios. Furthermore, computations regarding the traversing twin or any sometimes accelerating observer absent of the equivalence principle in gravitational fields, relies solely on the special theory of relativity instead of the general theory. There are two main approaches to this computation. The first calculates simultaneity surfaces based on light pulses, traceable back to Hermann Bondi's K-calculus concept. The second, albeit more technically complicated, computes how the traveling twin gauges the time elapsed on the stationary twin's clock. A succinct outline of this approach is documented in a separate section. We must also consider that the perceived time difference stems from the twins' different routes through spacetime. We can illustrate these differences by associating an individual clock with each twin. One remains stationary, and the other travels with the spaceship. The journey can be categorized into 6 phases. These range from the ship's launch till its reunion with the stationary clock, with different stages of acceleration, coasting, and deceleration. Knowing that the stationary clock remains inert, the total elapsed time of the traveling clock is derived by integrating the function of the coordinate time over the journey's duration. The story mingles time, velocity, and relativity and discusses the differences in elapsed times between a stationary clock Q and a traveling clock K and a traveling clock key E. There are certain interactions between the variables E, A, and T which impacts this shift in time. To calculate the altered time of the traveling observer EAK in relation to the stationary observer K, a delicate equation is applied featuring the velocity Vt at time t. When only the variables measured by key U are accessible, a more complicated direction is followed. This involves ascertaining the proper acceleration of the traveling observer SE, which is self-measured, for the complete round trip. The Cauchy-Schwarz inequality aids in proving that the inequality dEd derives from the previous expression. This is further clarified using the Dirac delta function to demonstrate the infinite acceleration phase in the standard case of constant speed v during the journey. The narrative then pivots to a concept depicting twins, Bob and Alice, in a space station orbiting a massive body. While Alice remains stationary in the station, Bob sets off on a space journey and reappears when the station completes an orbit. On his return, a noticeable change in their ages occurs. Alice is now younger than Bob's. Journey involves not only a change in velocity, but also a recalibration of speed to align with the space station's orbital velocity. Finally, the text indicates that in an absolute frame of reference, the so-called twin paradox does not exist, underlining the abstract nature of our perception of time and the many variables that influence it. In 1911, Langevin stated that detecting a uniform velocity in the ether was not possible scientifically, but that wouldn't necessarily make the ether non-existent. In 1913, Poincaré's posthumous work reiterated his stance that physicists opting for new conventions were not strictly required to do so, but they found these conventions more convenient. In Poincaré and Lorentz's interpretation of relativity, which assumes an indiscernible but absolute reference frame, there isn't any paradox owing to the occurrence of clock slowing, length contraction, and velocity as real instances. This implies that someone in complete rest with the universe, or a potential either, would experience maximum timekeeping and unchanged length. All effects of Einstein's special relativity fit into this framework. However, this interpretation of relativity, which Wheeler refers to as ether theory B, didn't gain as much popularity as Einstein's theory that dismisses deeper truth beyond measurements across inertial frames. There's no physical test which discerns one interpretation from another. In 2005, Robert B. Laughlin, physics Nobel laureate, Stanford University, commented on the ironic circumstance where Einstein's groundbreaking work on the general theory of relativity ended up conceptualizing space as a medium, despite his earlier implications on non-existence of such a medium in special relativity. In the realm of special relativity, 1968, A.P. French suggested that without the framework of fixed stars and distant galaxies, such effects as the twin paradox wouldn't exist. Most physicists concur that an ultimate definition of an inertial frame may be one with zero acceleration relative to the matter of the universe.